In this tutorial, we're going to see how reverse debugging can be done using Undo's LiveRecorder. Before going into the details of reverse debugging, let's focus for a moment on why we should use it in the first place. Reverse debugging is a highly effective way of debugging applications, allowing us to remove the guesswork in defect diagnosis by debugging backwards from the moment of a crash or failure towards its root cause. In order for reverse debugging to work, we first need to be able to accurately and efficiently record a process's execution. Ideally, we would want to do this without having to modify the process's source code nor affect the way it executes. That is, not unless we want to test its robustness, such as through the use of LiveRecorder's thread fuzzing feature. Finally, if we have the technology for doing such recordings, then we also need a debugger that's able to replay them forwards and backwards. Next, we're going to present a high-level process for reverse debugging using Undo's LiveRecorder. The process consists of three phases. The first is to record the failing process using LiveRecorder. The second is to load the recording in UndoDB, which is LiveRecorder's reversible debugger. Finally, we will reverse debug the recording in UndoDB. As a demonstrator for this tutorial, we have chosen a program that produces a deadlock scenario. If we briefly look at its source code, we're going to find a couple of linked lists that are modified concurrently by two threads for the tester function. Access to each list is controlled through the locking and unlocking of their own mutex. Now let's run the program and see what happens. As can be seen, the program has entered a state of deadlock, neither thread progressing after the first few iterations. Having seen the program fail, we can start the process of reverse debugging. The first step is to produce a recording of the failing or faulty process. The quickest way to do this is to record it with the LiveRecord tool. This can be done as easily as calling LiveRecord followed by the path towards the program that we want to record. Since a deadlock has been reached, we need to explicitly interrupt the faulty process in order to allow our LiveRecord to save the recording. As we can see, LiveRecord has created a recording of the debuggee, so now we can proceed with the second step. Loading the recording in UndoDB. This is a straightforward process of starting UndoDB and passing the recording name as an argument. Finally, we can start the reverse debugging. From the output of the debugger, we notice that we are at the beginning of the recorded history. That's how UndoDB works. When it loads a recording, it sets the replay position at the beginning of the recording. In order to reverse debug, we can quickly jump to the end of the recording using the UGO command. UGO makes the debugger jump to another point in the debuggee's recorded history. In our case, we want to jump to the end of the recording, hence we will call UGO followed by the end keyword. The alternative is to replay the execution history, but this can be a lengthy operation in the case of very large recordings. Let's run UGO end. Now that we are to the end of the recording, the debugger output shows that along the way, two additional threads have been created during the program's execution. In addition, the main thread has been interrupted through a seek trap signal while running in a GIP thread time join ex function in pthread join common.c. Because we assume that the program was in a state of deadlock when the recording was generated, we can start the debugging by checking the status of its threads. For this purpose, we are going to use the Infothreads command, which prints information on the debuggee's threads. Our suspicions are confirmed. Both threads 2 and 3 are blocked in a lock-wait routine outside our program's context. Reverse debugging can continue by picking any of the two deadlocked threads and reverse executing them until we find the root cause. Let's start with thread 3. To better understand where we are relative to our program, we should check the contents of the call stack. We do this through the backtrace command, which prints relevant information regarding the call stack. From its output, we notice that the first stack frame related to our program is stack frame number 2. This is 2 frames above of where the recording has stopped. Stack frame number 2 refers to a list lock call, where the debugger tried to get a lock on the first list mutex. Further back in history, looking at stack frames 3 and 4, we deduce that the list lock call originated from an iteration inside the tester function when the list prepend function was called. Based on this information, we can hypothesize that the deadlock is due to a previous call to list log, which left the list in a locked state. But this contradicts our assumption that each function that modifies our lists correctly locks and unlocks the list it is working on. It would be useful if we could go back in history and see what function previously changed the state of this mutex. However, since we are currently outside the scope of our program, we cannot execute certain useful debugger operations, such as printing information or setting watch points, as these require that the symbols we're interested in are within scope. Consequently, we should replay backwards the program's history until we reach stack frame number 2. We can do this by using the reverse finish command. This command will reverse execute a program's history one stack frame at a time. In other words, it will take us back to the moment where the call to the function listed at the top of the stack was made. Let's do this now. We are now within the context of our program's history, inside the last call to the listlog function that was made by thread 3 before it entered the deadlock. The deadlock happened when calling the pthread mutex lock function, because the list we called this function on must have already been locked. Let's verify this hypothesis. We can see that inside its data object, the lock variable was already set to 1, hence the mutex was already set when the listlock function was last called. What if we could magically find out when was this lock variable previously changed? Well, we can actually find this out by setting a watch point on this variable. We will use the watch-l command. We set watch points using the -l option of the watch command so that the debugger will track all changes done to the memory address of the variable we are watching, meaning that the watch point will work even if the variable becomes out of scope, in our case, once we leave the listlock function. So let's set the watch point. Having set the watch point, we will now resume execution in reverse. If the continue command resumes execution in the forward direction, reverse continue will execute backwards until a breakpoint or watch point is hit, or until we reach the beginning of the recorded history. Now let's reverse continue. From the debugger's output, we see that the value of the lock variable was changed from 0 to 1 inside a call to a gipthread mutex lock function. However, if we check the backtrace, we can see that previously, our listlock function was called inside the listunlink function, which was called inside the tester function. In other words, The last time the mutex associated with this list was set was when, while inside the tester function, the list unlink function was called. This function locked the list but failed to subsequently unlock it. Let's see what happened in the list unlink function by going back to stack frame number 2. As previously shown, we will use the reverse finish command. For a better visualization, we will switch to the text user interface. Before continuing, we will disable watchpoint number 1 so that we can step over the list lock function without the watchpoint triggering. Now let's see what happens if we continue the execution. We will use the next command in this case to move one line of code at a time. So, the list unlink function returned before the list unlock from line 97 was called. A classic mistake in concurrent programming. In this tutorial, we have presented a high-level process for reverse debugging using Undo's LiveRecorder. The process is composed of 3 main steps: recording a process using LiveRecorder, loading it in UndoDB, and then reverse debugging it in UndoDB. In this context, key points are the use of reverse execution commands such as reverse continue, reverse finish, reverse next, in conjunction with the use of breakpoints and watchpoints that get hit when executing both in a forward and backward direction. This tutorial has exemplified the above process and commands by solving a concurrency issue in a demo application through reverse debugging. For more information, visit Undo's documentation page at docs.undo.io.